Thanks to Brilliant for sponsoring today's video.
Today we're going to answer a question which is often raised by students whenever they learn about the cross product. And that is, well, is there a four-dimensional cross product or a five-dimensional cross product or some sort of arbitrary dimensional cross product? And this is of course after, knowing that there's a three-dimensional cross product which has been presented to them maybe in a multivariable calculus class or a physics class. And there's a lot of ways to get at this question, but I think the most elementary one that I found is from this 1967 paper from the American Mathematical Monthly. Okay, so to get started, we need to put some conditions on the notion of a cross product. And I think these are the agreed upon axioms for a cross product on Rn. So here we've got vectors A, B, and C, which are n-dimensional vectors, and then we've got a scalar, or just a real number, and I'll call this lambda. And so the first axiom that this cross product should satisfy is the so-called skew symmetry axiom, or anti-commutativity. That says that B cross A is the same thing as negative A cross B. So you flip the order and you pick up a minus sign. So of course, the normal cross product is going to satisfy this axiom as well as all of the others, because you can really view all of these axioms as abstracted versions of the properties held by that normal three-dimensional cross product. Okay, so let's look at the next two axioms. So we have A cross B plus C is A cross B plus A cross C. So that's like some sort of distributive rule of the cross product over addition. And then we have lambda A cross B is lambda A cross B. In other words, you can factor out scalar multiplication in this cross product. But if you put these two things together along with skew symmetry, you get so-called bilinearity of this cross product. Okay, so another really important property, perhaps the whole reason the cross product exists in the first place, is its ability to produce orthogonal vectors. So to write that down carefully, we would say that A dot A cross B is equal to 0. Recall that vectors are orthogonal if their cross product, if their dot product is equal to 0. And then, well, there's going to be one more axiom, which its algebraic version looks kind of crazy, but it amounts to having this fact that the cross product of orthogonal unit vectors is a unit vector. But that boils down to this statement. So we have A cross B, or the length of A cross B squared, is equal to the length of A squared times the length of B squared minus A dot B squared. Okay, so now that we've got the axioms for a cross product, let's state our question. And that is, well, what are the possible values of n, this dimension of the space that we're working on? So before we really dive into this, let's look at small values of n. Let's maybe look at n equals 1. In other words, we have a one-dimensional space. So I'm going to write this. So we've got R1 is equal to the span of a single vector. I'll call that E1. But now let's maybe go ahead and take A and B inside of R. But that means that we can write A as maybe lambda 1 times E1. And then we can write B as lambda 2 times E1. But now let's observe that A cross B is equal to lambda 1 E1 cross lambda 2 E1. But then we can factor out that lambda 1 and that lambda 2. And that gives us lambda 1 times lambda 2 times E1 cross E1. Oh, but now let's observe that E1 cross E1 is the same thing as negative E1 cross E1. So that might seem like sort of a weird thing to write down, but what we did there is switch the order of the E1s. But of course, switching the order of the E1s doesn't do anything. But if we pick up a minus sign by not doing anything, then we must have the 0 vector here, because the only thing that's equal to its negative is 0. So that means this is equal to 0, which means this whole thing is equal to 0. But then since A and B were arbitrary things, we got A cross B is equal to 0. In other words, the cross product is identically equal to 0. Okay, well, that's good news. We've got a cross product on a one-dimensional space. Let's look at a cross product on a two-dimensional space if there is one that exists. So let's take R2 to be equal to the span of E1 and E2. And here we'll have E1 dot E2 equal to 0. In other words, they're orthogonal. And we'll have E1 and E2 both unit vectors. Okay, but then note that we know that E1 cross E2 is going to be inside of R2, but that means that we can write E1 cross E2 as alpha E1 plus beta E2. Well, because that's a basis for R2. But now we're going to look at two competing facts. So this first fact is the length of E1 cross E2 is 1. So we know that because the cross product of orthogonal unit vectors is a unit vector. But that's exactly what we have here, a cross product of orthogonal unit vectors. But the length of E1 cross E2, well, that's going to be the length of this alpha E1 plus beta E2. But, you know, you can really just think of this as the column vector AB, or I should say the column vector alpha beta. But the length of that is alpha squared plus beta squared, or the square root of that. But that gives us this equation, alpha squared plus beta squared is equal to 1. Okay, so we've got some rules on this expansion of E1 cross E2 in terms of the basis vectors. But now let's also notice this. We should have E1 dot E1 cross E2 equals 0. And we also should have E2 dot E1 cross E2 equals 0 by this axiom over here of production of an orthogonal vector. This second one, well, you might need to use skew symmetry to get it to look exactly like this, but that's okay. Okay, but now observe that this first one turns into E1 dot E1, well, the alpha length of E1 dot E1. In other words, this is alpha. And then E1 dot E2 is equal to 0, so that part goes away. So that simply gives us the equation alpha equals 0. But likewise, this bottom one gives us the equation beta equals 0 because we're dotting E2 into, well, this expansion right here. But now we have a major problem here. Notice we have alpha and beta are equal to 0, and we have the sum of their squares is equal to 1. But that tells us that 1 is equal to 0, which is a clear contradiction. Which means, well, there's no cross product in two-dimensional space. So we've got this nice, well, maybe it's not so nice. It's a very simple, trivial cross product in one-dimensional space, but there does not exist a cross product in two-dimensional space. Now, of course, what about three-dimensional space? Well, that has the familiar cross product. Let's recall what that is before we move on to a more general setting.
Hey there, I'd like to take a minute to talk about today's sponsor, Brilliant.org. While watching my videos is a great place to start, you get more out of learning by doing, and that's why I highly recommend you sharpen your skills with Brilliant. With Brilliant, learning isn't just a task, it's an adventure. Dive into thought-provoking courses designed to challenge and inspire, covering topics ranging from mathematics and science to computer science and beyond. Brilliant's enormous library of learning content allows active learners like you to explore a variety of topics and skill levels, and Brilliant will support you every step of the way. Whether you're a student striving for academic excellence or a lifelong learner hungry for new insights, Brilliant has something for you. Engage with interactive lessons, solve stimulating problems, and watch as your understanding deepens and your skills soar. You'll be able to master whole topics gradually in as little as 15 minutes per day by sharpening your problem solving skills. I recently started exploring their growing number of programming courses. It's a great way to learn how to use Python. There are no boring lectures here. You will learn with their hands on approach. Give it a try and see how much fun it is. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself to a unique hands on experience by going to brilliant.org/Michael Penn for a 30-day free trial and 20% off your annual premium subscription. Thanks once again to Brilliant for sponsoring today's video.
Okay, so for the three-dimensional case, n equals 3, we'll take R3 to have a basis of E1, E2, and E3. So we'll take those to be mutually orthogonal unit vectors. And then, well, I'm gonna set up this little like triangle or this circle, however you wanna look at it. And this is gonna be like our pictorial hint of how the cross product works here, or rule maybe. So E1 cross E2 is equal to E3, E2 cross E3 is equal to E1, and then E3 cross E1 is equal to E2. So if you follow the circle, well, that's how you define your cross product, or that is the rule for the cross product. Notice E2, E3, E1. And then if you go against the arrows, you pick up a minus sign, but that's built into skew symmetry. So let's observe that this is exactly what you might have seen in a calculus class or a physics class, where the notation, instead of being E1, E2, and E3, is I hat, J hat, and K hat. Where maybe, of course, those are the familiar vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, nice. So there we've got it. We've got a cross product in 3 dimensions. That's like our familiar cross product. Now let's move on to dimensions that are higher than 3. But I guess before we do that, let's prove some characteristics or some rules that the cross product must follow that can be built just from these axioms. And those will be some nice tools to, help us achieve our final goal of answering this question. Okay, so this lemma is going to be particularly helpful. And, well, it says a little bit about how the cross product is non-associative. So notice this second rule has a hint of associativity on the left-hand side. And then the first rule is about how the cross product interacts with the dot product. So let's start with the first rule, which I have with a red dot. So we have A cross B dot C is equal to negative B dot A cross C. Okay, so the trick here is to use this rule, this orthogonal production rule, where we replace B with B plus C. And, well, this A can be replaced with B as well, because notice that B dot A cross B is also equal to 0. I think that's pretty clear. So let's see, we've got B plus C dotted into A cross B plus C. So we know that must be equal to 0. Again, because this vector A cross B plus C is most definitely orthogonal to B cross C by, the rule that we just talked about. Okay, so now let's expand this out. So this is going to give us B plus C, and then that's going to be dotted into A cross B, and then plus A cross C. But then we can use the distributive rule for the dot product over addition, and that's going to end up leaving us with B dot A cross B plus B dot A cross C, and then plus C dot A cross B, and then finally plus C dot A cross C. Again, just from distributing all of that stuff out. But now let's observe that some stuff is automatically equal to 0 by, well, again, this rule right here. So for instance, B dot A cross B, that's equal to 0 because A cross B is orthogonal to B. And this C dot A cross C is also equal to 0. But now let's put this together. Well, we can subtract this b dot a cross c from both sides of the equation, and we'll have c dot a cross b is equal to negative b dot a cross c. That's almost exactly what we have up here, but we can use the fact that the dot product is commutative to switch this around to a cross b dot c, and then we have, well, this first red dotted rule. Now let's move into proving the second rule. Okay, so for the second rule, we're gonna start with this equation right here, but we're gonna take this equation and we're gonna replace b with b plus d. So let's see what that leaves us with. We'll have the length of a cross b plus d quantity squared is equal to the length of a squared times the length of b plus d squared minus a dot b plus d all squared. Okay, nice. But now, let's use some facts here. So this over here on the right-hand side is equal to a dot a times, well, b plus d dot b plus d. But that turns into b dot b plus 2 b dot d plus d dot d. So again, that's the expansion of b plus d dot b plus d, which is, of course, the length of b plus d squared. Okay, and then next we'll have minus, let's see, this is going to be a dot b all squared, and then minus 2 a dot b times a dot d, and then minus a dot d all squared. Okay, so that's from that. And then we can do something similar over here on the left. We can maybe push this a cross b plus d through, using the distributive rule over here. So that's going to give us a cross b plus a cross d, and then we need to square that, which actually means we need to dot product it with itself. Okay, so let's do that. So if we dot product this a cross b plus a cross d with itself, that's going to leave us with, well, a cross b dotted with itself, which is the length of a cross b squared. And then we'll have plus 2 a cross b dot a cross d. That's like the cross term. And then we'll have a plus d dotted with itself. So that'll be plus the length of a cross d squared. Good. And then we can expand out this right-hand side a little bit. So this a dot a and this b dot b multiplied together will give us length a squared times length b squared. And then after that, we'll have a plus 2 times length a squared times b dot d. And then we'll have next plus a length a squared times a length d squared. Okay, so we've expanded out this first term on the right-hand side. But then that second term is already expanded out. So let's just put that down here. So we have this a dot b squared minus 2 a dot b a dot d, and then minus a dot d squared. But now it looks like this is a total mess, but we can simplify it using this rule over here that we have. Notice that on both sides of the equation, we see something that looks exactly like this with an a cross b and with an a cross d. So those bits are going to cancel. So observe that we know that a cross b squared is equal to, let's see, this term minus this term. Again, by this axiom. So that means those will cancel down, so we can get rid of them. And then furthermore, if we replace b with d, we know this a cross d squared will be equal to, let's see, this a squared d squared minus this a dot d squared. So those will cancel as well. And after that, that leaves us with everything connected to a 2. So that means that we can divide both sides by 2, and we have this nice formula. Notice we have A cross B dot A cross D is equal to, let's see, modulus A squared, or length A squared, times B dot D minus 2A dot B times A dot D. Okay, so now let's take that, or sorry, that shouldn't be a minus 2 anymore because we divided both sides by 2. Okay, so now let's take that and see where it takes us. This is where we left off, and this actually holds for all vectors D. And now we're going to do a bit of a simplification. Let's observe that we can take this left-hand side and we can actually simplify it using number 1. So maybe I'll use this red underline and arrow just to mention that we're using this red dotted thing. And that's this red dotted thing where C is equal to A cross B. So that's going to leave us with something like this. We'll have minus A cross B, and then that's going to be dotted into D. Okay, nice. And you might say, well, that seems like we're missing some terms, but there are some terms that cancel out along the way using sort of facts about the cross product producing orthogonal vectors. I'll let you check those. And then on the right-hand side, we can like factor a dot D out of the right-hand side, and that gives us a nice expression. So then we'll have A dot A times vector B minus A dot B times vector A, and then all of this is dotted into D. But then since D is arbitrary, what that really leaves us with is this vector right here, this minus A cross B, is equal to this vector right here, which I'm underlining in orange. So let's just put these are the same. But now the trick here is to take these two things that are orange underlined, which we know are the same, where A is replaced with A plus C. Okay, so putting that in, we'll have negative, we have the vector A plus C, and that's going to be crossed into the vector A plus C, which has been crossed into B. And then over here on the right, we'll have A plus C dotted into itself, and then that's in the B direction, and then we subtract from that A plus C dotted into B, and that's in the A plus C direction. And now we're at the point where you repeat what we did before. So in particular, we're going to expand this out, and then after expanding out, we'll simplify, using the thing that we already know. And what you'll see is it breaks down to give you exactly this blue dot. So maybe that'll be a bit of a homework exercise to fill in those details. Okay, so now let's see where this takes us. So I put the result that we just proved down here, and I added something else to it. And that's simply a corollary to this blue dot, the second equation. And that is if A, B, and C are mutually orthogonal, then A cross B cross C is equal to C cross A cross B. And well, if A, B, and C are mutually orthogonal, then if you take any of their dot products, you get 0. And that would simplify this right-hand side to 0 pretty clearly, meaning that those two objects are the same. But then we have it. Okay, so let's look at a definition which will guide the next couple of steps. So let's say that B is a subset of Rn. For our purposes, it'll always be a subspace, but this is defined just as a subset. And we say that this is A cross stable if for all A in A and B in B, A cross B is in B. So if you cross it with something from A, you land back in B. So if A were like the whole space Rn, then this would be similar to the notion of an ideal in ring theory or the theory of associative and non-associative algebras. Okay, so let's look at the following result. So if we have a subspace B of Rn and it's A cross stable, then the orthogonal complement of B is also A cross stable. So let's see how we can do that. So let's suppose that we've got a vector which I'll call C in B complement. But let's really quickly observe what that means. So that means for all little b inside of B, we know that B dot C is equal to 0 because C's got to be orthogonal to everything inside of B. So now let's take any vector A, and this is going to be inside of A. And that's because we need to show that B complement is A cross stable. And then let's look at the following. So it'll be B dotted with A cross C. So we hope that this is 0 because that would tell us that A cross C were also in B complement. In fact, we'll get that very, very quickly using, well, this rule over here from the lemma that we just proved. This is minus A cross B, and then this is going to be dotted into C. But observe that we assumed that B was A cross stable, but that means that A cross B is inside of B. But then if you dot anything inside of B with C, you get 0 because C is in the orthogonal complement of B. So here you get that this whole thing is equal to 0, but that's exactly what we need for A cross C to be inside of that orthogonal complement, finishing this proof. Okay, so let's move on to our next result. Now for one of the most important results that's going to help us answer this question, well, it was down there, it's not there anymore, about what dimensions allow for the cross product. So let's suppose that we've got a subspace of Rn, which we'll call A, and it's closed under the cross product. So it's in a sense a subalgebra with respect to the cross product. Let's also take an orthonormal basis. So that's a basis of unit vectors, each of which is orthogonal to all of the rest. And that is A1, A2 up to AK. So this is k-dimensional. Then for any unit vector B in the orthogonal complement of A, then the set B, B cross A1, B cross A2 up to B cross AK is an orthonormal set. But let's recall, if you've got an orthogonal set, well, that set is automatically linearly independent. That's a standard fact from linear algebra. But orthonormal is just a special type of orthogonal. That means this set is automatically linearly independent. But if we've got k plus 1 vectors that are linearly independent inside of a complement, a orthogonal complement, I guess I should be careful to point out that these are in the orthogonal complement of A. That'll follow pretty quickly from our last result, but we will prove it. Then that means that the dimension of the orthogonal complement of A is bigger than or equal to the dimension of A plus 1. Because, well, that might not be all of the orthogonal complement, but that's k plus 1 vectors. Okay, so this is going to happen in 3 steps. So the first thing that we're going to prove is that, yes, these land in the orthogonal complement. So let's do it like this. So let's take any set, or I should say vector A in A, and let's look at A dotted into AI cross B. But that's essentially the same thing as dotting A into B cross AI, just by skew symmetry. Okay, so let's observe that we can use this rule over here. That seems to be a favorite rule at the moment, to write this as minus B dotted into A cross AI. But then let's observe that A cross AI is inside of A. So there, we've got that inside of A because, well, A was this closed subspace or this cross subalgebra. Okay, but then B was in A complement. We're dotting B with something inside of A, so we get 0. But then that's exactly what we need for this, let's see, AI cross B to be in A complement. But then that means that, yes, this set is a subset of A complement. Okay, so now let's look at the next thing. So it's a subset of A complement. Now we want it to be an orthonormal set. So we need them to be unit vectors. But now let's observe that AI is orthogonal to B, and they're both unit vectors. But then let's recall that this, let's see, 1, 2, 3, 4, fifth axiom down here was equivalent to the cross product of orthogonal unit vectors as a unit vector. And so that means that, yes, we can apply that here, and we have AI cross B is a unit vector. That's all we need to do. And, well, we could work that out if we wanted to, but notice that the length of AI cross B, that'll be the length of AI, the length of B minus their dot product squared, but their dot product is 0. These are both 1s. There you have it. So now let's show that all of the vectors in here are orthogonal to each other. That'll finish off everything that we need here. So let's take AI cross B and we'll dot it into AJ cross B. But now let's switch some things around. This will be -1 squared times B cross AI and B cross AJ, just by skew symmetry, but -1 squared is clearly equal to 1, so that doesn't do anything. So we switch 2, which is like switching none. Okay, there we have that. And then, well, we've got this interaction rule of the dot product with the cross product, which we can use here. So let's use this rule right here. And that's going to turn this right-hand side into minus, let's see, we'll have B crossed into B cross AI. And then all of that is going to be dotted into AJ, like that. But now notice this is just a triple cross product thing. We can use this rule over here where just one of the B's is equal to C. But whenever we do B cross C, we get 0. So let's see what that's going to simplify this whole thing down to negative, and then we'll have B dot AI, and that's going to be in the B direction, and then minus B dot B, and that's going to be in the AI direction. And then we dot that whole thing with AJ. But luckily we know something about these values. We know that B dot AI is equal to 0 because those are orthogonal. We know that B dot B is equal to 1 because, well, that's a unit vector. So we end up in the end with AI dotted with AJ because those two minus signs cancel. But recall that this was an orthonormal set, so that means that this dot product is equal to delta ij. In other words, it's 1 if I and j are the same, and it's 0 otherwise. But that's exactly what we need to finish proving that this is also an orthonormal set. Okay, so let's see where we can go from here. Okay, so now we're going to explore a little bit. So let's say we have Rn where n is strictly bigger than 3. And then let's take E1 and E2 inside of Rn where their length is equal to 1. So in other words, they're unit vectors and they are orthogonal to each other. So their dot product is equal to 0. And then from here, we're going to set E3 equal to E1 cross E2. And then, well, what you can check here is the following, and I'll leave this to you. If we set A equal to the span of E1, E2, and E3, then A with the cross product is essentially the same thing as R3 with the cross product. So it's a copy of the three-dimensional cross product inside of Rn. Okay, and then let's also notice this. So since n is strictly bigger than 3, we know that A complement is not equal to 0 because, well, we've got things outside of A because, again, this is 4-dimensional space or higher. But then by our previous result, we know that the dimension of A complement is going to be bigger than or equal to the dimension of A plus 1. So that means it's bigger than or equal to the dimension of 4. But then also, we know that n, which is the dimension of Rn, is equal to the dimension of A plus the dimension of A complement, which is bigger than or equal to 3 plus 4, which is equal to 7. So immediately we see that there's no 4, 5, or 6 dimensional cross product because of this fact right here. So next up, let's exhibit a 7-dimensional cross product and see if we can find any at higher dimension. So what do we have so far? Well, we've got cross products in R1, R3, and R7. We haven't seen the one in R7 yet, but I'm about to present it. None in R2, which we showed sort of by hand from scratch. And then using an argument involving the orthogonal complement, we derived the fact that there's none in R4, R5, or R6. And then, well, after this board, we need to finish off with the question, what about Rn for n bigger than 7? So is it possible to have an 8-dimensional, 9-dimensional, a 10-dimensional cross product, or a 123-dimensional cross product? Well, we'll see. But before we do that, let's look at the 7-dimensional cross product. So it's kind of defined in terms of this Fano plane is what it's called. And it's related to the octonions, which we have other videos on. So here I've got 7 vectors on the board, E1 through E7. And how you read this is if you're going in the direction of the arrows, you could pick up a plus sign. If you're going in the opposite direction, you pick up a minus sign. And each of these edges is seen as a loop. So for instance, E1 cross E3 is E7 because we're going in the direction of the arrows. E3 cross E6 is minus E4 because we're going against the direction, and then we loop back around to E4 because we've got this loop containing E3, E4, and E6. Then also like E2 cross E3 is E5, and then you can pull others off if you want to. Let's see, E1 cross E6 is negative E5, and so on and so forth. Okay, so now let's finish off with our final question. What about 8, 9, and larger dimensional cross product? Now we're ready for it. We're going to prove that if n is bigger than 7, there is no cross product on Rn. Well, meaning that, well, we've got the answer to a question. There's only a 1, 3, and 7-dimensional cross product. But how do we finish this thing off? So here's what we're going to do. We're going to take a copy of R3 with the cross product, which is equal to the span of E1, E2, and E3 inside of Rn. So we sort of saw that we could always do that, and now we're going to do that. And let's maybe set this equal to the vector space A. So A is the copy of R3 with the cross product inside of Rn. And then let's also find a unit vector, and we'll call that unit vector B inside of the orthogonal complement of A. And then after that, we're going to set B equal to the span of the following set of vectors built out of all of this. So we have E1, E2, and E3. And then after that, we'll have B, and then B cross E1, B cross E2, and B cross E3. So this is going to be a 7-dimensional subspace of Rn. And in fact, this subspace is going to be isomorphic, or the same as the 7-dimensional cross product space. Okay, and then let's also notice that by our earlier proposition, this is in fact an orthonormal set. And in other words, it's a set of orthogonal unit vectors. Okay, nice. And then, well, we know that the dimension of B is 7, like we said before, and we know the dimension of the ambient space is larger than 7. But that means that we can take something in the orthogonal complement of B. So I'll call that thing C. So we've got C, which is in the orthogonal complement of B. And then, well, let's set D equal to B cross C. And then, well, since we've all got unit vectors here and they're all mutually orthogonal by construction, Well, what can we do here? Well, this B, C, and D form an R3 triple, if you will. So it forming an R3 triple means that we have the following two things satisfied immediately. C cross D is equal to B, and then after that, D cross B is equal to C. So again, that's an R3 cross product triple, if you will. And now we're going to make use of this thing down here, this magenta dot, as well as a version of this blue dot right here, where two of these vectors are the same. So I'll point that out when we use each of these. Okay, so now let's look at the following calculation. So let's take EI, where, that's one of these up here, E1, E2, and E3. We're going to cross that with B. And then we're going to cross that with EJ, which has been crossed with C. Okay, now let's take C and write it as D cross B. So here we'll have EI cross B, and then this is going to be crossed into EJ, which itself is crossed into, let's see, D cross B. Okay, nice. And now we can use this rule right here with appropriately chosen A, B, and C to rewrite this in the following way. And this is not going to look like dot products, but essentially what you can do is translate them all into dot products using this formula and see that you will get the same thing. So here we'll have EJ crossed into D, and then that's going to be crossed into, let's see, EI, which is crossed into B, which itself is crossed into B. So we've got something like that. Okay, and now we're just going to simply bring this EJ cross D down, and then after that, we're going to take the rest of this and express it using the dot product, using, special choices of A, B, and C here. And that's going to give us something like this. So we're going to have B dot EI, and that's going to be going in the B direction, and then from that we need to subtract B dot B, and that's going to be going in the EI direction. But now here we'll use the fact that B dot I is equal to 0 because those are orthogonal, and B dot B is equal to 1 because that's a unit vector. Then we can bring out this minus sign and we're left with minus EJ cross D, and then that's going to be crossed into EI. But then we can apply skew symmetry here as well as this rule over here to get us to D cross, let's see, EI cross EJ. Okay, nice. So now let's bring that up, and then I'll present a similar formula, which I won't prove, and then we'll see how that finishes everything. Okay, so there's the equation that we just built. Similarly, we can show that EJ cross C cross EI cross B is D cross EI cross EJ, but that's the same thing as we have up here. But I've swapped things down here. I've swapped those two things in parentheses. But then by skew symmetry, these left-hand sides are negatives of each other. But then the right-hand sides are equal. But if the right-hand sides are both equal to each other and negatives of each other, that means that it's equal to 0, because the only thing that it's its own negative is 0. So that means we have D crossed into EI cross EJ is equal to the 0 vector. But then also, we know that D is orthogonal to EI, D is orthogonal to EJ, EI and EJ are orthogonal, but that means we're taking the cross product of a big collection of orthogonal unit vectors, meaning that the length of D cross EI cross EJ is equal to 1. So simultaneously, we've got something that's the 0 vector and thus has length 0, and something that is a unit vector and thus has length 1. But that's our contradiction. But what did we really contradict here? Well, we contradicted this ability right here to take some sort of C from B complement. That shouldn't have been possible. In other words, B complement should not have existed. But the only way that B complement existed was the fact that n was strictly bigger than 7. So, well, what does that mean? That means it's impossible for n to be strictly bigger than 7 and to have a cross product. So there you have it. We've just finished proving that the only cross products exist in 1-dimensional space, 3-dimensional space, and 7-dimensional space. And that's a good place to stop.